As we expect the common collector amplifier, the gain is equal to 1. So we'll be getting the gain equal to 1. So gain point of view, what we are expecting, that is simulated and we got it. And now another parameter, I have to calculate the CC amplifier, not only giving the gain 1, like we expect the main requirement of the common collector amplifier is input resistance should be maximum than common emitter amplifier. So where like a common collector amplifier should be having that high input resistance than the common emitter. So now we have to simulate it. And to calculate the R input, what I do is the same network which I have it, I'll be doing the simulation once again. So what I do is I have to calculate the first parameter is the gain. We got it, it's around 1, it's okay. I have to calculate the input resistance now. So there is a procedure to calculate the input resistance. What I do is I will be going with the Thevenin's theorem now. I will be going with the maximum power theorem, right? As maximum power theorem says, if there is a source resistance of Rs, I have it, and there is a load resistance of RL, we have it. If I connect my source, there is a maximum power transfer when source resistance equal to the load resistance. So from this theorem, I can go with one analysis where to calculate the input resistance. So let us suppose this is my circuit where common collector amplifier, let me connect it over here. This is my common collector amplifier which I am trying to connect it here. I don't know the input resistance of this one. It might be that R input is something, yes. So what I do is I will be keeping a test resistance over here, RT, and I will be varying, and I will be giving my as it is input 10 volts over here. So where depending upon the strength of these two components, this is my input resistance of the common collector amplifier, this is my RT which I am trying to adjust based on my requirement. So initially if the resistance over here is less, if RT is this one, and R input and V input. So when I give like input is 10 volts, input is 10 volts. So RT when I make it 0, so the drop across the RT is VRT is equal to 0. Means whatever you give the 10 volts, it will be shared to my CC amplifier itself, my circuit itself. So V input of my circuit, it is going to be 10 volts. So now same 10 volts again and again I am giving, and I am trying to verify when the resistance is increased. When the resistance increased, when there are two persons who are not strong with the with compared to each, V is very weak, so 10 volts took by R input. 10 volts took by R input. So now in the another case, when the resistance is increased, the test resistance increased, the moment when both are at the same strength, both are at the same strength. If the resistance of this one is, let us suppose 10k, so he is having zero resistance, so that 10 volts will be going to this one because he is very strong. So in moment when he is also 10k, so I adjust to 10k. Let's suppose initially adjusted to 5k, 5k. So there will be two. There are like out of if let us resistance is resistance around 10k. Resistance around 5k. There will be three pots. Two pots will be going to this one and one pot will be going to this one. Means 6.6 will be shared to this one and a 3.3 will be shared to this one. So based on the strength, the voltage will be shared. What I do is I will be calculating my input voltage around 10 volts over here, and I will be verifying the voltage across this one. So I will be keeping one probe over here. I will be taking the voltage at this one, and I will be verifying at 10 volts which I get it, and what will be the voltage drop to this person. So I'll see the moment when 10 volts which I apply. So the moment when he will get it around 5 volts, it means so half of the 5 volts, remaining 5 volts will be shared to this person itself, right? 6%. Half of the voltage will be shared to this person itself. It is around 5 volts. So now I feel that I should not increase the resistance beyond, because that resistance of the input is it reached to the level. So it's of 5. So I will be increasing to the same level at one point. So VR1 is equal to 5 volts, and the V input also it becoming 5 volts. So that's what I will try to do the simulation, and I will be calculating the input resistance of common collector amplifier out here. So first initially I will be making the common collector amplifier, the resistance is 0. Okay, and I will see so input is around 10 volts, because like 5 into 2 divisions 10 volts. Output is also same. When I keep the resistance over here 0, whatever the 10 volts I gave it, 10 volts will be shared to this one. So I got it around channel A, it's around 10, and channel B also 10. So the strength of the resistance is 0. Now I will be increasing the resistance over here, strength of this resistance over here. So I will be making it to 1k. So 1k. So the moment it reaches to the 1k, reaches to the 1k, so there are around like 2 divisions need to be shared. My input signal need to be shared for the 2 divisions. So now it is not shared to the 2 divisions, means around 9 volts. We got it around 9 volts. Means the 1k resistance which I made it some strength of that input I keep it, so that he is taking some part of the signal. So out of 10, some part, this much part is taken by the 1k. So what I do is I have to make this resistance value big, such a way that half of the part input signal need to be taken by him, only half need to be shared to this one. So I will be doing that. I will be increasing that. Instead of like 1k, I'll be keeping to 7K for next case. So I'll do the simulation once again, and now if I see, so it's not up to 5 divisions, it's not 5 volts, it is around 7 volts. Yes, so 3 volts is shared to him, and 7 volts is shared to him, right? Both are not same, both are not at same strength. I have to go with next case where I have to increase the strength of this person further. So around 10 I keep it. So now if I see, exactly 5 volts I got it here, 10 volts which I apply. So when I apply 5 volts over here, when I apply 5 volts over here, when I apply 10 volts over here, so here I don't know what is shared, but I got it around 5 volts over here. So obviously 5 volts will be dropped to that resistance which I keep it, test resistance which I keep it. So out of 10, shared by this one is 5 and shared by this one is 5, in the sense the resistance offered by this network is equal to this network. So 10 kilo ohm is the test resistance I got it, for which I got like half of the voltage, maximum power is transferred, where the source resistance equal to the load resistance, where I can assume that the load resistance will be equal to the 10 kilo. So now our input for that particular circuit, common collector amplifier, is around 10 kilo ohms. So now that we will see that in the theoretically the value of that input resistance for the common collector amplifier, when you do the calculation for the input resistance, the network over here, let me try it once again. There will be a emitter resistance of around 2.4 kilo. Theoretically, let us calculate that input resistance calculation, where AC analysis, when I do, VCC will be grounded. So over here R1 comes parallel with R2, connected to the ground, and this network will be as it is, 2.4 kilo ohms, right? What I want to do, I wanted to bring into this network, right? So I will be erasing this total network and the equivalent network. Let me draw where at a emitter resistance of 2.2 kilo, when it is converted into the base, it need to be multiplied with the scaling factor of beta. It might be like 1 plus beta, but approximated to the beta. So now the base resistance which I have to connect it, the value which is approximately, there will be a beta times or 1 plus beta times extra current. So that extra resistance of that many times, around beta times of 2.2 kilo I have to connect. Yes, the resistance of R1 is around like 18.3k, parallel with 22k R2, parallel with the resistance which we got it. Beta value I took it around 100 times of 2.2 kilo. So let me show the beta value of 100. So here if I give double click and go with the edit model, where I can see the forward beta of around 100, and based on the value of the beta itself I am trying to do the simulation. So from these, it is around 9.9k, parallel with 100.2. So 100 into 22 is around 220. 220 into 9.9 divided by 229. It is around, we got it around 9.47 kilo ohms. So that resistance which we got it around 10k, where I got the max equal strength. So we calculate the input resistance around like a 10 kilo ohm practically, and theoretically we got it around 9.47. So now next job is we need to compare with the common emitter amplifier, where like a simulation we have done it for the common collector amplifier and calculated the input resistance around 10k, and which need to be greater than common emitter amplifier. So now let us do the simulation for the common collector amplifier in the similar manner, where this is the simulation for the common collector amplifier. So where I keep the input resistance around 4.9 kilo ohms. Let me simulate it. Here like common emitter amplifier, where I have to observe one thing: whatever the input we apply, where at the output without clipping, without distortion, I have to get the faithful signal. Whether I'm getting or not, I have to verify. If the faithful signal is not getting at the output, that whatever the input resistance you calculate, that will not be a correct value. So make sure we have to connect my CRO at channel A and channel B. So this is my channel A and this is what my channel B, where I wanted to verify the voltage at this one, the voltage of this one, and parallelly I will be doing the calculation for the voltage value over here by the another CRO. So I will be observing the three samples and three waveforms at a time, whether like output waveform is correct or not, without distortion I'm getting or not. So if I do the simulation for this one, where input signal which I apply is 20 milli. If I give like 20 volts in the previous case, the circuit will not be amplifying, where like I will be getting a distortion. So what I do is, the minimum voltage which is required to do the simulation for the common emitter amplifier around 20 milli, let me use the 20 milli over here, where the input is this one. So here like a V input is shown here, and this voltage is shown over here, and this voltage is shown over here. Yes, so input is around 20 millivolts applied. 20 millivolts is applied. So where my input signal over here need to be generated, which need to be the exact off. So where I'm expecting around 10 milli. So until I get 10 milli, I have to make this resistance need to be adjusted. So what I do is I'll be keeping this resistance value 0.5k of kilo kept over there. So let me check. So there is a output is getting distorted or not. Every time I have to check it. So it's not distorted, so that I can go with the calculation. Input is around 20 milli. Input is around 40 milli. Input is around 40 milli. What I get? I need to get around 20 milli. But here is not 20, it's more than 20. So here at input 2 divisions, I have to get it at 1 division. My signal over here should be accommodated in the 1 division. Until that, I have to increase my resistance. I have to go with the 1k. If I keep it 1k, where I will be getting that so where at 1 kilo, let me stop. Where at 1 kilo, exactly what I apply input signal, where at 1 kilo where at 1 kilo where at 1 kilo where at 1 kilo this is my input signal, which is called not input, source signal. It is around 20 per division, so it's around 40 millivolts which I applied. So here this is the point I'm expecting it should be off. So it is around 2 divisions, it need to be at a 1 division. So where this one is around 20 milli. So the moment when I get a 20 milli, it means whatever the 40 you apply, so 20 is shared to this one and 20 should be shared to this one. So when it is shared exactly, the resistance of your common emitter amplifier, this is my common emitter amplifier, it will be the equal value of the resistance which you have applied. So from this is common emitter amplifier with R input is, so it's exactly 1 kilo ohm, and we have calculated for the common collector amplifier, R input is around 10 kilo ohm. So with compared to the common emitter amplifier which we got a input resistance here, it is around 10 times. So that is the reason where at input section I prefer the common collector than common emitter. So I will be using common emitter for amplification in the middle stages, but in the input stage where I expect the input resistance need to be maximum, so that's why I prefer the common collector amplifier. So now next task is we have to verify the common emitter amplifier input resistance theoretically, is it correct or not. So let us verify that. So this is my common emitter amplifier. Let me copy that. If it is a common emitter amplifier, where I have to calculate the input resistance for this one. So when I calculate the input resistance, AC input resistance, all capacitors need to be shorted. AC analysis when I do it, this one also shorted. So where my transistor circuit, if I redraw, this one will be connected to the ground, and R1 R2 network, it is around 20k in parallel with 7k. So this will be a total circuit now, right? And when I replace this one with the H period model, H period model will be this one, HIE, and so beta times of HFE times of IB. Yes, this is what my emitter. So if I replace it over here with respect to transistor, so where emitter terminal is connected to the ground, so let me ground, and this is my base terminal, so the base terminal is connected to this one. So this is how HIE will be connected. HIE value is around 1.1, typical value of H period model says the HIE value is around 1.1, and now 7k parallel with 7k kilo ohms parallel with the input resistance of the circuit is 7k parallel with 20k kilo ohms parallel with 1.1 kilo ohms. So this value will be 7 into 20 divided by 27. This value will be 5.18 kilo ohms parallel with 1.1 kilo ohms into 1.1 divided by 0.28, 5.29. It is around 1.07 kilo ohms. So which we have calculated theoretically it is around 1 kilo. It will be a practically we have calculated 1 kilo ohms through the simulation. We got it around the same. So from this theoretical observation for the input resistance for the common collector amplifier and common emitter amplifier and the voltage gain for the common collector amplifier. These three things covered over here. The voltage gain of the common collector amplifier, it is equal to the 1. This is what observed. And input resistance of the common collector amplifier, it is around 10k. This is observed. And input resistance for this one, it is observed around 1k. So this is theoretically and practically observed. This is also theoretically and practically observed.